This is the second revision paper. And how do you identify them? I have right down over here number 2. And I will give you the solution right now for this question. Number 1, Simon is practicing hammer throw. He spins the hammer in the horizontal circle of radius 1.6 meter, rotating once every 1.55 seconds. So this is the period. And assume Simon arm made a straight line with the hammer handle. At this speed, the hammer handle made an angle 20.4 degrees to the horizontal. Calculate the tension in the handle wire of the hammer. So number 1, and I should do is that I sketch it out. Approximately this is the picture whereby the hammer making 20.4 degrees to the horizontal and spinning at this rate. Now the first question, find the tension. How do I do it? We have to realize that this hammer will exert a force of gravity. A force of gravity will be exerted on the hammer, give you W. At the same time, you have tension in the wire. And then tension in the wire, this is the part that we understand. Since it's making an angle here, we can resolve it to be one component is this, that's pointing upward, and this will be T sine 20.4. And what I can tell about these two forces, they will be equal because they are in uniform circular motion. Therefore, my T sine 20.4 is equals to W. And how do I find tension? I just take the W divided by sine 20.4. And what is W? It is mg. M is 7.26, G is 9.8. So that's my expression for my W. And followed by 20.4, sine of this is a number. And the answer here, it is about 204 Newton. So this is one way that you can use to solve this question. One more method is that you can resolve it to the horizontal to get the FC. It is possible because you know the period here. You can try it out and you should get the same answer. Let me move on. How does the angle of the hammer handle change if Simon increases his rate of rotation? So how does this angle here change if the speed here increases? Of course, when we do the experiment, we know that if you increase the speed, this thing will go up even higher and this angle here shall be smaller. But how do we explain it in terms of mathematically? So what I can do is that I can make use of this equation, square Rg tangent theta. This one you can find in your manual. However, I have to remind you, this theta here in your manual and in general all cases, it is good by assuming this theta. This is derived when you assume the theta is at here. Yeah. So let me scroll. This is at here. Okay. So let us do something about this. Let us first of all define the theta here. Alright, by right need the question asking what will be this angle here change. But let us analyze what happened with theta if I increase the speed. Okay, so this is it. I can first of all expand the term of the v square because it's 2 pi r over t. If I expand, I get 4 pi square r square over t square because Rg tangent of theta. Yeah, and then what happened next? Simplify a little bit. My tangent theta is equals to 4 pi square r. I can cut off on power. Equals to g t square. Yeah, perhaps I don't want in this one. I want to change it even because I want to make the t square as my subject. I can redo this, just a simple step. Now let me try to make a relationship between r and theta. Looking back into the picture, r and theta. R is here. Okay, use r is here. Theta is here and the length is here. The length of the pendulum, which is fixed. So look this equation, the theta r, and now I can link it up by using sine theta. Sine theta opposite r divided by L. So let me write down over here. My sine theta is r over L, and r is L sine theta. So I'm going to plug this thing into here, and plug in what do I have? Okay, so this is L sine theta divided by G tangent theta. Okay, and let us simplify, because you know that tangent theta is sine over cos. If I divide over here, you see sine and sine will cancel and the cos will go up to give me this. Okay, and what's happened here? This entire term here, they are constant. So when I increase the rate of rotation, my t will decrease, yeah? And if my t will decrease, automatically my cosine theta will decrease. Okay, so cosine theta decrease, if you remember the function, is something like this. So when my cosine theta decreases, you will see that it happened when the theta here getting bigger and bigger. Okay, so I can conclude that my angle here will increase. So the theta here will increase. Let us look back into the diagram. The theta here is increasing. If this is increasing, of course the other end here, the angle here will decrease. Respect to the handle, respect to horizontal will be decreasing. So to answer this question, let me say again that my conclusion here is that the angle of the handle, angle of the handle will decrease, because this theta here is referring to the angle at the top. If this is increasing, on the other hand here, the question asking how does this angle change? If this increase, this must decrease. So answer here will be decrease. Okay, will decrease. Yeah. So this is one of the long explanation. Okay, let me move on. You throw a ball at the wall at speed 25 meters per second at angle 40 above the horizontal. The wall is at distance 22 meters from release point of the ball. How far above the release point does the ball hit the wall? How do you solve this question? You have to first of all find the time of flight. How much time is required to travel 22 meters given the speed with the angle? So number one is that I will use my Sx to find my time of flight. The ball will travel 22 meters and my Ux is 25 cosine of 40, because the Ux and cosine, yeah, in this case. Time here is 1.15 seconds. And how do I find how far above I can use Sy? Okay, given that Uy is 25, in this case is sine 40 for Uy, and time here is 1.15 seconds. Okay, so the time of flight, and at the back here is minus 4.9 t squared. G is negative 9.8. Don't forget to square. I have an answer of 12.0 meter above here, the release point. And how about the ball displacement? Half a second after the release. So this is really this is not easy, because displacement is a vector. In order to do this, we have to find Sx and Sy. Yeah, this is by the end asking for the entire S vector. We can do it by solving its component Sx and Sy. So this Sx here is 25 cosine of 40. After 0.5, you should plug in 0.5, don't plug in 1.15 here, because asking 0.5 is 9.58 meter. Of course, it's horizontal, I can assume to the right. And how about Sy? You have to find that out as well by using the same formula, but with the time changed to half a second. It's 25 sine of 40, 4.5, and in the end still minus 4.9, 4.5 squared. This value here happened to be 6.81 meter, and you have to combine them using Pythagoras theorem. Sx squared, Sy squared, take the surd. I'll leave it for you to figure it out. So this 11.8 meter, and the rest, how about the angle? Because it's the vector, you have to tell me the angle here, the direction. You can use the inverse tangent. Okay, and in this case Sy over Sx. Okay, take note that if both terms are positive, especially on SY, you can safely know that this angle is above the horizontal. Above the horizontal, SY 6.81, my SX is 9.58. I have the answer 35.4 degree above the horizontal. So do give me the full description. If by any chance you still do not understand this, please look for assistant, please look for me or your friend. Next, how about the velocity of the ball when it hit the wall? So again, velocity vector, V vector here, you have to find the Vx and Vy when it hit the wall. So again, this is not so straightforward, you have to find Vx. Vx here, okay, this 25% for T because it's a constant. Value is about 19.2 meter per second. On the other hand, Vy, this one you can use this projectile equation to find it. When it hit the wall, remember it is time from the question A is 1.15 seconds. And the Uy here is 25 sine of 40. Okay, this is negative 9.8, this is 1.15. I have my answer to be 4.80 meter per second. So again, find the magnitude, combine them using the Pythagoras theorem. Vy square, Vx square, combine, take the square root of it. 19.8 meter per second, that is the answer. And again, about the angle here, you can use the inverse tangent of Vy over Vx. And since Vy is positive, you can safely say that it is above the horizontal here. But you have to plug in the value. And this 4.8 divided by 19.2 happen to be 14.0 degree above the horizontal. So that's the quick answer, yeah. For the last component, when it hit the wall, has it passed the highest point in the trajectory? Justify your answer. So how do you do this question is that you can find the time to reach the maximum height, yeah. How do you find, you can use this equation. Okay, because at maximum height you do know the Vy is 0, and when you launch it, it is 25 sine of 40 for the Uy. Okay, solve this time here. The time required to happen is 1.64 seconds. And since the time to hit the wall is 1.15 seconds, it's lesser than 1.64 seconds. So what do you deduce? I'm pretty sure you know that the answer is that not yet past the highest point. Make sense? Time to reach the maximum is this here, and it hit the wall at 1.15, so it has no chance to go to the maximum height. So that's the answer, not yet passing the highest point. Alright, and the next question here, you have to find the gravitational force due to Earth on mass, position at x and y, same mass here. Remember this one is drawn to scale. Estimate the ratio of Sx to Fy. So when I'm doing this, do the measurements, you can do the measurements. I have my answer here. The distance from A to X here, I have about 4.6 here. Whereas my center over to Y, I have about 6.9 here. Okay, and what I can do next is that I can make up some ratio here. Ratio, perhaps I call Fx. It is GMM, mass of Earth, mass of small object. Doesn't matter what's the value yet, just make a term over distance. And also in this case, I will want to stick to non-SI unit for a moment because I'm finding the ratio. Yeah, so SI unit or not is not that important. Whereas my Fy will be GMM divided by the distance over here is 6.9 squared. So you have to know ratio of what, the x to y, so you must be strictly Fx to Fy. You cannot make it the other way around. Fx to Fy. So I will divide these two terms here. This for Fx and Fy is this. You realize this these two m's are not important. Okay, and if I want to rearrange it, look at it properly. It is 6.9 square divided by 4.6 square. Okay, so if what you have over there, you can use your calculator. It's approximately, actually this is 3 over 2 to the power 2. Okay, this is 9 over 4. So the ratio here is 9.4. Yeah, so this is the answer. Alright, so that's drawn to scale. Please do the proper measurements. Question 4. I perhaps want to skip this because this is a little bit advanced for you at this moment. Alright, so I should skip this. Your question about torque is a very fundamental, so I don't involve this level of difficulty yet. Alright, and let's move on to question number 5 here. Okay, you can read the questions. So you have to draw the arrow to show the forces acting on the parcel when passed through the highest point. At the highest point, what are the forces labeled here? Okay, so remember parcel, you have the force of gravity, the weight over here. It's a mass, you have to label it. Don't just put arrow without putting anything. It's not accepted. And one more force over here acting is, of course, from the floor of the van. It exerts a normal force. That's it. These two are the answer. Okay, these two are the answer. Okay. What's this? Okay, don't know what's. Okay, I cannot remove this. This is disturbing me. Okay, so hold on a minute. This one. How do I remove this? What is this? Okay, now I cannot even scroll down. Okay, let me stop for a while to get this done. I will continue afterwards.